STP is spanning tree protocol, which we also discussed in our NA class. But this time, we are going to go much more flavors or different versions or advanced spanning tree. Spanning tree protocol is it's good. It's a good protocol. In layer 2 domain, what it does is it avoids loop. Avoids loop. There are very there are very too many chances for a loop to happen in layer 2. Whenever there will be a broadcast or multicast, there are chances for loop to occur. Definitely loop will occur in layer 2 if there is a broadcast or multicast. So we need some loop prevention mechanism. So STP is the loop prevention mechanism in layer 2 level. Spanning tree protocol. It's like a tree that spans around the network, that spans around the topology. And if the tree if the tree happens to come to the same place via some other interface, then it identifies that there is a loop. Let me repeat. There is a tree called BPDU, Bridge Protocol Data Unit, which spans around the topology. This tree will be spanning around, running around, going around all the possible links in the topology. When the BPDU from this switch, when the tree from this switch comes back to the same switch, then it identifies that there's chance for loop. So immediately it kickstarts the STP here and makes STP to go and pick a point where it can put a tree and block it so that the loop won't occur. Because there is a block, it won't move further. Because there is a block, it won't go back to the same switch from where it came. That's the idea behind spanning tree protocol. Selecting a spot to block when there is a redundant link. So whenever we have switches like this, there are chance for loop to occur. The BPDU that is sent from switch 1, this direction and this direction, goes to switch 2, and from switch 2 will take the BPDU, update, and then send it via the other interfaces. And this switch 3 receives it, takes it, and updates it, and send it via the other interface. And this BPDU comes back to the same originator from where it originated. Similarly, this packet that went like this reaches switch 2, and switch 2 sends back to switch 1. So switch 1 is the originator of the packet. This is what we called, this is how the loop is identified by the BPDU. So the packet that is going around is not a user's packet. It's not a ping packet, it's not a ICMP or a telnet packet or a FTP packet. Before the ICMP, telnet, FTP hits the internet interface, before the user traffic start using the layer 2 domain, this packet will be generated by every switch. Each and every switch will generate this packet called BPDU and send it via all the interface to reach the other switches. The other switches take those BPDU and update themselves with the neighbor switch information. We call it as bridge ID, and sends it to the other switch. Likewise, every switch will send their BPDU every 2 seconds. Every 2 seconds they send the BPDU, and this BPDU makes the switch to understand that it is undergoing loop, or there are chances for loop to occur. So before the actual loop occurs, this BPDU goes and blocks one of the port. By doing so, when a user traffic comes, when a broadcast from a user comes in, that broadcast may go like this, and it will not come back. Why? Because there is a block. Now, one very important thing that I want to say here, which is very important, what it is, even though there is a block, BPDUs will be still going and coming just to maintain this block. Very important. This block state is not going to block BPDU. They block only the user traffic. To maintain this block, they keep sending the BPDUs on every interface, even on the block port. The BPDUs will be still going on. That is the one which maintains this block. Alright, so bridge protocol data unit is the one which is used by spanning tree protocol to recognize a loop. And STP immediately kickstarts if there is a BPDU coming back to the same originator and finds the best spot to block and blocks it. By doing so, it prevents loop. Now, how it chooses the best spot to block, those stories we learned in the previous CCNA track. But again, I would like to quickly brief on it and then take you to the next version of spanning tree. Now, this spanning tree, you and I are not going to enable STP. Spanning tree protocol gets kick-started automatically when BPDU from a switch goes and comes back to the same switch via some other interface. It goes via one interface and comes via another interface. Then there are chance for loop. So STP will get kick-started. Now, how STP prevents loop? That's what we are going to see. How STP prevents loop. One, we saw BPDUs are the one which is helping to identify a loop. Yes, anyone has any question?
No, sir.
Okay, so it is the BPDU the one which helps to identify the loop. Now, let's take 3 switches. It's the same case even if you have 10 switches. If there is a redundant path to reach back, if there is a path to reach back via some other interface, then loop will occur. Even if it is 10 switch or 6 switch or 3 switch. This is the minimum number I'm taking, 3 switch. Now, how STP selects the best spot? How STP picks a spot? Based on the bridge ID. Bridge ID or switch ID. Now, every switch has got, see, bridge or switch ID both are same, okay? Bridge, in CCNA you learned, bridge and switch both are layer 2 device. So this bridge ID is combination of your priority, VLAN number, and the MAC address. Priority, VLAN number, and the MAC address. This is what the bridge ID means. Priority, VLAN number, and the MAC address. So every switch has got a MAC address. Let's say the MAC address of this is AAA, this is BBBB, and this is CCCC. So what happens? MAC address comes here, AAA, and by default all the interfaces are in VLAN 1, so VLAN 1. And here the priority, by default the priorities, 32768. This is the default priority. Likewise, for this switch, what will be the bridge ID? 32768, VLAN number 1, BBB. For this switch, what will be the bridge ID? 32768, VLAN 1, CCCC. Now what it does is, first it compares the priority. That's the higher order bit. See the priority. It's a big number, 32768, but it's the same number. Spanning tree will choose a switch as a root switch. First it will choose a switch as a root switch. Before going to block, it will select a switch as a root switch based on the lowest priority. Lowest priority. Now when it see the priority is the same. So next what it will do is, it won't check the VLAN. VLAN is also same. Now it checks the MAC address. So definitely one MAC address will be smaller than the other one. So in our case, this switch 1 has got the lower MAC address than switch 2 and switch 3. So if the priority is a tie, if there is a tie in priority, only then it goes to the MAC address. Lowest or smallest physical address, MAC address. Okay. This is for what? This is for root bridge selection. Root bridge or switch selection. So this lowest priority of how one switch knows about the other switch lower priority and MAC address. They share BPDU. From the BPDU that is coming from switch 2 and switch 3, switch 1 knows about the other switch's priority and the MAC address. So switch 1 says, I have the lowest priority, lowest bridge ID, because my MAC address is smaller. So this becomes what? This becomes a root switch. This becomes a root switch. And these switches becomes designated switches or non-root switches. This is a designated switch or non-root switch. So root switch election is based on the lowest priority. If there is a tie in priority, then it picks the lowest MAC address. Switch with the lowest MAC address becomes the root switch. Now, all interface on a root switch will be designated to forward. They don't block. Next is the root switch election is over. Now these two switches will try to find the low cost path. Low cost path. For what? To reach the root switch. Low cost path to reach the root switch. Let's say the cost here is 4 and here is 19. Cost here is 4 and cost here is 19. So this switch will say, switch 2 will say, this port will be the root port. So every switch will try to find the lowest cost path to reach the destination. So switch 2, if it goes like this, it is 4. Let's say cost here is 2. For switch 2, going like this is cheaper. 2. If it goes like this, it is 2 plus 19, it is 21. Too costly. So it picks to go via this interface. Let's say this interface is faster than 0/1. It goes via 0/1 instead of going via 0/2. Right. So this port, what it will be called as? It will be called as root port. Why it is called as root port? This is the port that connects to the root switch. Now, if this is the root port, then this will be called as designated forwarding. It's a forwarding port, designated forwarding. Now, this switch, what it will do, it will find the lowest cost path to reach the root switch. If it goes like this, the cost is 19. If it goes like this, it is 2 plus 4. 2 plus 4 is 6. Very cheaper. So what happens is, this port will be elected as the root port. Root port for this switch. This is the root port for this switch. Okay, this is the root port, and the designated forwarding port, this is the root port, and this is a designated forwarding port. This is the only one which is left. So this will go to what? Blocking. This will go blocking state. Now the loop is prevented. Now in case, if I have something like this, one, 2, 3, and the MAC address here is A. Now if I have something like this, and if the cost is same, and the priority is also same, you know, it is 32768 is the priority on all the switches. And now you know which will be the root switch. This will be the root switch, and this port will be designated to forward. Now the non-root switches will try to find the shortest path to reach the root switch. So going like this is 19. If it goes like this, it is 19 plus 19. So it won't go via fast Ethernet 0/1. It will go via 0/2. So it choose to go via go via fast Ethernet 0/2 because the cost is 19. If it goes like this, it is 19 plus 19, costly. Alright, so this will be what? This will be root port. Likewise, this port will be a root port. It will now, you understood this one, low cost path. Now because there is a tie in the path cost now, you see, 3 is going like this, 19, this way 19. Now there is a tie in the cost. Now it need to decide whether a block can happen here or here. Which one will block? That's a decision that it needs to make. What it will do is, it'll see the lowest bridge ID again. Lowest bridge ID again. The lowest bridge ID means, the lowest MAC address. Because there's a tie in the priority, the lowest MAC address. So this port, this switch port will be designated to forward, will not block. Spanning tree likes all small MAC address, small bridge ID, priority. So it will not block this one because it likes it. This one, C is the big one, which it doesn't like. So it will make this as what? Block. So this is different. This is another scenario. Now let's take one more scenario. These things, anyway, we discussed in CCNA. I am repeating again so that you will recall one more time, and we will get into the newer spanning trees. Let's say we have switch A and switch B. Is there a chance for loop to occur here? Yes. So I just randomly picked an interface. Randomly I have taken some interface names, and we have two switches. And let's say the priority on this is 32768, and the priority on this is 4096. This is the priority on this 4096. So you know very well that after priority only comes what? The VLAN number and then the MAC address. The MAC address of this is AAA and this is BBB. The MAC address of this may be lower than the other one. So this is bigger MAC address and this is smaller MAC address. But still this is the root switch. Why? Lower MAC address. The higher order bits are smaller. The higher order bits here is bigger. So if the higher order bit is tie, only then it will go to the lower order bits, which is MAC address. Here the higher order bit is lower than the other one. That's why we say the first priority is given to what? Low priority. The first preference is given to the priority because it is in the higher order bits. Okay, now what happened is we got AA and we've got BBB. Though BBB is bigger than AA, still it cannot win the election because BBB has got the lower priority. AA couldn't win the election. So this is the root switch. Root switch means both the interface will be designated to forward. Designated to forward. Okay, this is designated to forward. What is next? Next is one of this port should block. Which one to block? So what these two ports will do, they will try to find the shortest or lowest cost path. Low cost path to reach the root switch. But unfortunately here the cost is same. Fast Ethernet means 100 Mbps. 100 Mbps speed link, cost is 19. This is industry standard default STP cost. It is STP cost. No need to ask how here. If you have 1 GB, you got 4. If you got 2 GB, what am I writing? 1 GB is 4. Yeah, 2 GB is, no. 1 GB cost is 4. 10 GB cost is 2. These are all predefined STP cost. Now here, because you got fast Ethernet, the cost is same. 19 and 19. Cost is same, there is a tie. Now based on what this will decide? Based on the port priority. This is not switch priority, this is port priority. If this port number is 11, you got number 11.128. If the interface number is 2 here, you got 2.128. If you got 1 here, 1.128. If you got 2 here, 2.128. Now what it will do, it will see lowest incoming port priority. See, incoming means what? This is the non-root switch. Non-root switch. So this switch will do, this will verify, this will see which interface is giving the lowest priority number. This is giving 1.85, 1.128. This is giving 2.128, which is lower. This is lower. So this is lower means this port will be a root port to talk to the root switch, and this will be the blocking port. Blocking port. That's it. So these things we learned in our NA class. You can take 4 router, 5 router, wherever redundant paths are there. This is how the blocking spot will be selected. Next thing what we are going to learn is called Cisco's spanning tree, called Cisco per VLAN spanning tree. Per VLAN spanning tree. Cisco's PVST. PVST and then PVST plus, both are same now. PVST plus. Per VLAN spanning tree. This one, what we saw now is a default IEEE 802.1D standard, which is industry standard. By default it is there. And what you are seeing now is a per VLAN spanning tree. Whose design it is? It is Cisco's design. Cisco has got its own spanning tree protocol. What it is, it runs a separate instance of spanning tree for every VLAN. In this the problem is, if I have 100 VLANs, for all 100 VLANs there will be only one STP, only one spanning tree. But on all Cisco switches, this is the default. On all Cisco switches, this is the default. It is not IEEE 802.1D. It is not this. It is PVST, per VLAN spanning tree. This is the default on all Cisco switches. Now what is this? It will run a separate instance of spanning tree protocol for each VLAN. For each VLAN it runs a separate instance of spanning tree. So 100 VLANs if I have, I will have 100 spanning tree. For every VLAN there will be a separate spanning tree running. There is an advantage as well as a disadvantage here. What is the disadvantage? Disadvantage is too many spanning tree protocol is running. So too much of process utilization. That's the disadvantage. What is the advantage? I can do load balancing. How? VLAN based load balancing you can do. VLAN based load balancing. What it is? Let us say I have 4 switches, just for example. Assume we have 4 switches and they are connected like this. This is switch 1, 2, 3. MAC address is 111, 222, 444, 333. Assume these are all the MAC address. Fast Ethernet 01, Fast Ethernet 02, Fast Ethernet 01, Fast Ethernet 02, Fast Ethernet 01, Fast Ethernet 02, Fast Ethernet 01, Fast Ethernet 02. Right. Now if I have VLAN 10, VLAN 20, VLAN 30, VLAN 40 created. So this is one PC, this is another PC, this is another PC, another PC. Connected to this switch. Likewise, I got here VLAN 10, VLAN 20, VLAN 30, VLAN 40. Now, which switch will be elected as a root switch if the priority is 3, 2, 7, 6, 8 common on all the switches? If you don't change it, then this will be the root switch because of the lowest MAC address. I told you 111 is the MAC address, 444 is the MAC address, 333 is the MAC address. We know MAC address is 48-bit size, but here for example we have taken this small number. So this is the root switch. So if this is the root switch, both this port will be forwarding, and this will be the root switch for all VLANs 10, 20, 30, 40. And assume there is a block here. Cost is 19. Definitely the block will be there only. Block will be here. So block is here now. Now, if you ask me how the traffic is going, for all this VLAN, the traffic goes like this. No traffic goes like this. No traffic goes like this. All traffic 10, 20, 30, 40 needs to go via this top switch. It has to go via the top switch, the upper one. But if I have per VLAN spanning tree, which is Cisco proprietary, per VLAN spanning tree, what I can do is, I can make this switch as a root switch only for VLAN 10 and VLAN 20. I'll allow this to be a primary. This is the primary switch for VLAN 10 and 20. And I'll make this one as the primary for VLAN 30 and VLAN 40. Because there's separate instant of spanning tree running, I can do this. I cannot do this in the previous version. So what I'll do, I'll go to this switch and give the low priority only for these two VLAN. So this will become the root switch for 30 and 40. So 30 and 40 will go like this. They will not be blocked. Only 10 and 20 will be blocked. Likewise, 30 and 40 will be blocked here. 30 and 40 will be blocked here, and 10 and 20 will not be blocked. So what you have here, we have all the switches busy in forwarding the traffic, and all the links we are utilizing. If you don't do this load balancing, all traffic goes only via the upper switch, not via the lower switch. So to do load balancing, what you can do is, you can say these two VLANs are primary on this and these two VLANs are primary on this. And when this switch fails, I want all to be fallen on this one. So what I'll do is, I'll say for VLAN 10 and VLAN 20, you are the secondary. And here I'll say for VLAN 30 and VLAN 40, you are the secondary. That's all. So anything happens, if this switch goes down, this will take the primary role for all VLAN, or if the top switch goes down, the bottom switch will take the role of primary for all the VLANs. Now today I'm going to show you how to do this. Today also I'm not going to do the lab because I don't have time to install the packet tracer, which I don't have now. So what I'll do is, soon after this class I'll send you the previous class video on this per VLAN spanning tree, load balancing, the command that I use, primary, secondary. You can give command. When you give command, it will reduce the size of the priority number from 3 to 768. It will reduce into a smaller size, meaning it will subtract 8096. If you say secondary, from 3 to 768, it will reduce 40968 to 8192. So 4096. I am sorry, what I'm doing. 1024 2048 4096 8192. Okay, see, very important. When I say primary for 10 and 20, what really happens is, from 32768, 8192 will be deducted. When you say secondary, from 32768, 4096 will be deducted. Now tell me, which one will be the lowest value? This one will have the low value subtracted after subtraction than this one. So this one will be higher than this one. So whichever the switch that has got lower priority, that will be the root switch. So if I have primary command given for VLAN 10 and 20, this is what happens. If I have secondary command for 30 and 40, this is what happens. So for VLAN 10 and 20, this is the switch that has got lowest priority than any switch. The other switches are got 3 to 768. Likewise here, when I say primary for 30 and 40, this is the switch that has got lowest priority, because from 3 to 768, (8192) is subtracted for this. When I say secondary, 32768, 1024 is subtracted. 4096 is subtracted. So this will be the secondary and this will be the primary. So by doing so, we can do load balancing if we have per VLAN spanning tree. Alright. So quickly I'll be doing this thing in next class, but let's go and learn the next version of spanning tree. Is there any doubt in per VLAN spanning tree? You can ask me now. Rapid spanning tree. See, what does rapid means? Fast. RSTP, we call it as RSTP, rapid spanning tree protocol. The above two versions that we saw about STP, they are timer based, meaning they undergo different state. In the previous version, whatever you learned in normal STP and PVSTP, they will be in a state called learning state. First of all, it will be in a state called listening state. For listening state, it will take 15 seconds. 15 seconds, it will be simply in a state called listening state. In this state, what it will be doing, it will be listening to all the BPDs that is coming, and it won't take any decision, just listening. Even if there is nothing to listen, it will be in that state. and then it will get into learning state. That is another 15 seconds, where it learns all the topology, MAC address, and then it will be keep on learning. Even if there is nothing to learn, it will be in a state called learning the MAC address and the priority of other switches through the BPDU. And then it will decide on which port to block and which port to forward. For the decision making from block to forward or from forward to block, it takes another 15 to 20 seconds. So if you see the total, it's around 50 seconds convergence time. So when the primary link goes down, it takes around 50 seconds for this block to be made as forwarding. So for this 50 seconds, whatever the packet that is trying to go will get dropped. Very slow convergence. That's why they designed another protocol called Rapid Spanning Tree Protocol, RSTP. Now this rapid spanning tree is really rapid. It is faster. Why you call it as rapid? Because this is not timer based. It is not timer based. It just waits for something to learn. If there is something to learn, it learns and then immediately goes to forwarding state. And in rapid spanning tree, we don't have a block port. We call it as alternate port. Now this rapid spanning tree is not timer based and there is no block port. Instead we have got alternate port. Alternate port is different. Alternate port is different from block port. See, what is this block port? Here it was blocking. When the primary link goes down, it needs to listen and learn the new topology, MAC address, and then only it will, after learning, it will go to forwarding from block. Whereas if it is, instead of blocking, if it is alternate, every switch knows that this is the alternate path. In the normal STP, who is the dictator? It is the root switch. Root switch is the dictator. Whereas here, every switch knows the role of the link, everything. So when the primary link goes down, immediately the switch will go and make this as forwarding. Very fast. All the MAC address which is already going this way will be swapped from this interface to this interface and the traffic will go well this way. No learning and then turning into forward to block. Very fast convergence. You may lose one or two packets. If it is too much of traffic, you may lose 2 packets. Mostly without any loss of packet, the conversion happens. Whereas here, the older version, 50 seconds of wait time, you will miss at least 5 packets if it is very less traffic. If it is more traffic, even 500 packet also you may lose. If it is normal STP. If it is rapid spanning tree, mostly you won't lose any packet. This is also demonstrated in the video that I am going to send you after this class. Rapid spanning tree. Rapid spanning tree is not a timer based and every switch knows the status of the ports and the link. When a link goes down, immediately the switch which is near to this alternate port will make this as forward, immediate. No learning and all. Immediate. It was listening and it found that there is no BPDU coming from. There is a disconnection, so there is no BPDU coming between this. So immediately this switch will say, hey, no BPDU from this guy. So this guy will turn this as forwarding. Immediate. Very fast convergence. Rapid spanning tree is rapid. Now in rapid spanning tree, whenever we learn rapid spanning tree, we'll also learn something called port fast. Port fast. What is port fast? Do not wait for BPDU response. Very simple. Do not wait for BPDU response. Don't wait. So some says port fast means port fast disables spanning tree. No. That is for easy understanding. People say port fast will disable spanning tree. You cannot disable spanning tree anywhere. Don't disable spanning tree. Spanning tree is good. So when we have something like this, loop causing network, you enable rapid spanning tree. That is good. But when you have computers connected here, whenever a BPDU loss happen, they will immediately send the BPDU asking for alternate path via every interface. So this interface will immediately, it will come from blocking to forward, no doubt. But the BPDU that went this way needs to respond back. The BPDU that goes to the PC needs a response back from the PC to decide on this blocking to forward. To make this block to forward or alternate port to be a forwarding port, every link should respond. These links will respond because they are connected to switch. They know what is BPDU. But PCs don't know what BPDU is. Even though rapid spanning tree is faster, it cannot decide very fast because the switches are waiting for PC to respond to BPDU. When there was a change happening, when BPDU was sent to the PC, PCs were not able to respond back to the BPDU. So the switch will wait till the timeout happens, and then only it will decide to make this as forwarding. To avoid that, only on the port that connects to the end host, very important, only on this port where the PC is connected or servers are connected, you go and enable spanning tree port fast. This is the command. Go to the interface and enable spanning tree port fast. When you say to this interface spanning tree port fast, what it will do, whenever there is a change happens in the topology, the response, BPDU response will not be expected. It won't wait for this PCs to respond to the BPDU, response to the topology change. It won't wait. So what indirectly you are saying is, you are telling to the switch on this interface, don't expect any superior BPDU. Don't expect anything whenever change happens. Don't expect anything there. Decide without waiting for this interface. Decide on changing the port role without waiting for the host to respond. That's the meaning of port first. Now this port first you should not enable where? On this links that connects to switch. Why? You are saying don't expect BPDU to be responded. Spanning tree is blocking based on the BPDU response. So if you enable port first on this trunk port where the BPDs are very important, or BPD response are all very important, you are actually making spanning tree not to function normal. So be cautious when you enable port first. We need to enable only on the host port. We call it as edge port, only on the edge port, host port which is connecting to the end device, not on the port that connects to a switch or a hub or a concentrator kind of device. Is there any doubt in rapid spanning tree? Shall I take that as no? Okay. So, hope you understood about normal STP spanning tree protocol, per VLAN spanning tree protocol, and rapid spanning tree protocol. Now we are getting into another type of spanning tree protocol called multiple spanning tree protocol, MST. Multiple spanning tree protocol, MST, multiple spanning tree protocol. What it is? It is like this. When you enable rapid spanning tree, per VLAN spanning tree also gets enabled automatically. For every protocol, for every VLAN, there is a separate instance of spanning tree working very fast because it is rapid. When you enable rapid spanning tree, per VLAN spanning tree gets enabled. For every VLAN it will be faster. The previous one was simply per VLAN spanning tree, and this is rapid, means faster per VLAN spanning tree. So what is the drawback in the previous one? Previous one was faster, but there is a drawback. What is it? For every VLAN. So if I have 1000 VLAN, 1000 spanning tree it needs to run. So too much of process utilization and load on the device. To reduce that, what we are allowed to do is we are allowed to decide how many spanning tree can run. Let's say I have 1 to 1000 VLANs. Now I am allowed to say STP instant 1, first instant of STP will run from VLAN 1 to 10. 1 to 10 VLANs, instant 1. Instant 2, 11 to 20. Instant 3, 21 to 250. Instant 4, 251 to 1000. So I can define how many spanning tree can run. So for all these VLANs, only one STP. That is STP number 4. For all these VLANs, only one STP. That is STP number 3. So we can say how many instances of STP I want, and which instant is mapped to which VLANs. Instant 2 is mapped to 11 and 20, 11 to 20. Now I can do load balancing even here. Same story. What I'll do, I'll go to this switch and say, for instant 1, for MST instant 1, you are primary. For instant 2, you are primary. For instant 3 and 4, you are primary. So all VLANs from 1 to 10, that is instant 1, 11 to 20, that is instant 2. So all those 20 VLAN traffic will go like this. And all the VLAN between 21 to 1000 will go like this. So MST not only allows you to reduce the number of spanning trees, it also helps to do load balancing. So this is about multiple spanning tree protocol. So this is what the entire story about MST. What is left is the configuration part. So after this class, I'll be sending you the video on MST, on per VLAN spanning tree, on rapid spanning tree. Please go through that and come back on Monday. On Monday, we are going to learn about VTP, DTP, layer 3 switching. Yes, so this is our plan. Hope it was an informative day for you. You learned something new. Thanks for joining today. See you on Monday. Take care.